大一点啊，讲者也是英文的，所以待会儿可能要考验一下大家的专心程度。那一样哈，大家准备一下，我们随时要开始了。OK OK。好，那我是今天的主持人，我叫丽叔。那有几件事先做一下事先的宣导。哎呀，长度正头了。好，第一个网络的使用，这个在每个地方都一样。我们有3个 AP 在这一间会议室里面，麻烦你依照你的座位哈，最好不要互相冲突啊。啊，有3个 ID，你可以自己选择一下。那另外呢，还有就是在大会规定啊，应该说这个场地规定，请不要在会议室里面饮食。他有给我们一个开放的机会，就是讲师可以啊，其他人如果你觉得愤愤不平，欢迎报名，下次我们安排你上来，你就会享有这个特权。好，那另外一个当然是一个礼貌的问题，请你把你的手机关机或者形成震动。那经过昨天一天的经验，我们发现似乎在会议室里面你也不太能接手机，因为收讯太差。好，然后展示一下，因为是7月，所以你不要说亮亮亮，这个广告不知道给我们看过，网络上流传的，吵什么鬼啊？千万不要这样子啊！现在是飘飘乐。好，那接下来我们就要准备一下，把你的热情展现出来。我们需要各位的，好，你看，如果没有这个反应，我们会切到下一张投影片。如果看到这一张，也是一样要做一样的动作。那接下来，来宾请掌声鼓励，欢迎我们的讲者 Roger Frater。
I think I'm supposed to start. Good morning. I'm talking about the GNOME Memory Profiler. It was not created by me, but I thought it's useful, and so I've opted for maintaining it and developing it further. I'm pretty sorry this is going to be a technical talk, and if I'm losing anyone, we can try to pick you up, but it might or might not work. But you can get in touch with me later if you still have questions. So our agenda is first of all figuring out what the GNOME memprof is actually about, and then we will look in how it's working. So we will have to see how C applications allocate memory. Then we need to figure out how to get a backtrace to see who was allocating the memory. This leads us to the problem: how do we intercept a function call to an external library, and how to get a backtrace from this. And finally, we are concluding with a backtrace. So, what's the summary? So, what is GNOME memprof? It's a tool to analyze the memory usage. We can visualize the allocations to see how much was allocated over time with a time graph. We also have a view done by someone else to visualize memory fragmentation, which works nicely if you only have a small program, but in case of WebKit, it's going to be so slow that it's currently unusable. And to not make it as dry as possible, I'm actually just showing you the application. So I've started. I've started the GNOME Memory Profiler, and this is the application, and I'm looking at events. So right now I have allocated everything in memory from this bar, and this one was actually mapped but is currently returned. And I do have this graph. So over time we see startup, we have a small peak, and then we free some memory, and then we're going up again, and here. So if I'm opening any file, do I have something in my history? So if I'm opening these slides of my conference, we see that it actually allocates a lot more memory in peak, and it displays the window on the different screen. So we see that just by opening, we do have this peak in memory to open the PDF, and then it goes down, and then it goes back. And we can press profile to actually generate a profile of the application, which is now going through all all allocations, and it's going to visualize them. So we can see in self how much memory was allocated in each function. So the pixmem image crate bits has allocated that many bytes. You have to divide by yourself to get the number of kilobytes and megabytes. So and you see that crate bits was calling pixmap image allocate, and in the caller view you're actually seeing who was calling this function. And by double clicking you can see this graph extends, and you see the possible callers of this function. So Cairo image surface crate was actually calling pixmem. So we can click again, and we do see that Evins has been loading a libpdf document plugin, and right now it doesn't know anything about it because I don't have symbols for this backend. So just by clicking here, I'm not going to have a lot more information. I'm just seeing that events, document render, document load, and document thumbnails have all allocated memory. So if you have debug symbols of all your libraries, you can trace back every allocation of your application and be able to see who is the main offender, and if you see it. There's also a leaks display which uses the Böhm GC algorithm to find out which memory was leaked, but I actually think it doesn't really work. We have seen the time graph, which is actually now stable, so it doesn't leak more memory or allocates more memory over time. And we do have this graph which actually shows you which areas of memory were allocated, and like here's the stack, here's the heap, and which actually we're missing a legend to explain which colors are used for which kind of things, but you can actually, if you know the colors, figure out which areas of the memory are allocated or were unallocated but not returned to the system. So if you have a lot of places where you have had memory allocations but the block is too small to return it to the system, you can see it here and probably do something about it by using gslice or just allocating memory in the same sizes. So I'm just going to quit this application, and now we're going back to the slides and figure out how it's actually working to do this. So memprof works by tracking calls to malloc, new, gslice, and other things. It generates a backtrace for each allocation, and it forgets about the allocation when it's freed. So the biggest limitation with this approach is that an allocator actually works by allocating memory from the kernel, which is either using mmap to allocate an anonymous non-shared piece of memory, or the sbrak call, but this is not intercepted by memprof. So if you use a custom allocator in your application and it doesn't have external linkage and all calls go directly to this custom allocator, you're not going to see the allocations in memprof. This is an example of a problem with WebKit where we have a custom allocator which has internal linkage. So you're only seeing half of the allocations that your application is really doing. But if you're aware of this problem and you know you don't have a custom allocator, it shows you every allocation your application is doing. So the memory allocators like glibc or others actually use these two calls, but we're not interested in these to allocate. So we are only caring for malloc, free, new, delete, and allocate arrays and delete arrays. And we also have some special knowledge for gslice and others to generate a more meaningful backtrace. So we know of glib functions that allocate memory and start the backtrace at this function instead of the malloc call, which is done from the allocator. So how do I find calls to malloc? One approach would be to to change every call from malloc and make it call a new function and make it call a new function and try recompile the result, or I can try to instrument glibc to build a custom glibc which calls my application, but in general both approaches are not practical. We want to look at the memory allocations of an existing application right away without recompiling the system, so we need to have a different way. So the way is to use a ELF feature to preload symbols. So I don't know. So how many of you have ever used LD preload to load a library? Anyone else? Do you know the concept, or? So the idea is to So the idea is to create a. Let me switch again. So the idea is to just let me switch the colors off. So we just write a small application to preload a symbol. So we want to have our own implementation of malloc instead of the other one. So we need to remember the actually malloc call. So I call it real malloc, and it's a function pointer having the signature of malloc. And then I'm providing a malloc function with the same signature as used by the system. And in here I can check if real malloc, like so if real malloc is 0, I will have to find the real symbol of malloc. So I can write it like this: real malloc, assign it to dlsim, and there's a glibc function called, or a special handle for the dynamic linker, which is rtld next, which helps me to find the next symbol called malloc. So I can write it like this, underscore. And luckily my current glibc doesn't allocate memory, so I can use a printf from inside the malloc function. If it would allocate memory, I would have like an infinite loop and it would crash, so I can write real malloc here, and at the end I'm just calling the so at the end I'm just calling the real malloc function with my member, and then I need to compile it as a shared library. I'm calling it libpremalloc2so. One has to use position independent code because we're preloading, and then I'm handing it the source code, and it doesn't know about rtld next, so I will have to go back here. First, it's a GNU feature, so I need to define GNU source, and I need to include a header file called dlsymbols, and I need to write it properly as well. So of course it's called differently, so I'm using the man page to find it. So it's warning that it doesn't know my printf. I should include standard IO to have the right signature, but I'm lazy. And finally I can use LD preload SO, and now I can execute any other application which allocates memory. So ls would be the most simple application to execute, but it doesn't allocate memory at all. So we